Thank you. Thank you. Yeah, I met Paul, I think it was 2004. We were on our way to a salt mine in Saline, Kansas. And at that time, I was studying humic materials. And we're driving along, and he said, "You mean humates can do that? Yeah, they can detoxify. Yeah, they can increase CEC. They can do all this and do all that." And by the time we came back, he had pretty well developed a new livestock product. And there's, and I can tell it's still being made. So that's how we got our start. Right now, I'm on retainer by Paul. I think we've been doing that for close to 10 years now, something like that. And I like working with Paul because he figures out that something's working out in the field, out in real life. And as a product developer, as I am, it's usually the other way around. You know, it's like being an artist. You make 10 things and one of them sells. And that's always, and some people call product development just another form of bleeding, which just means it's really expensive. And then you hope you get a product after years and years of research and field trials. But Paul would call me up and say, "Hey, Lawrence, this is working. Why is it working?" And that's how we got started. So I'm going to explain this photograph later on in the presentation. But there's a lot going on in here. This was actually a slide from one of his previous meetings, and when I saw it, I knew right away what those little bits were on this fungal hyphae. Those are calcite, bits and pieces of calcite crystals. So I knew right away when I saw this, and it's kind of indicative of where we went. Now, when Paul says that everything is microbial driven in soil systems, that's absolutely right. The emphasis since World War II was put on more NP and K and your plants will grow. And the problem with that is it's environmentally unsound. It puts more carbon dioxide in the air. It releases way too much nitrogen into the environment. There's all kinds of drawbacks to it. In order to fight the diseases that are brought on by over-application of synthetic materials, we have to bring in drugs for plants, basically, and those drugs are supposed to cure the problem, when the problem was actually created by what we were doing for the last 50, 60 years. And my formal training was that. You know, my formal training was in order for something to be plant available, it has to be soluble. And that is so untrue, actually, it turns out. That's what I learned after studying this for quite a few years. For starters, we usually rely upon a soil test of some sort. And that typical soil test will show us organic matter, which is, by the way, organic matter tests are non-standardized. So if you find if you're using an organic matter test in one lab, you might get a different answer in another lab. But that's true of just about every method out there. But these are pretty good numbers. And we look at the phosphorus P1, P2. If a soil is over 7.4 pH, automatically, then that's when they use the Olsen analysis for phosphorus. Potassium here is stated, this is right up here. If you read the real fine print, neutral ammonium acetate exchangeable. That describes the method that was used to extract the material, not how the material was analyzed. That's how it was extracted. And then we usually look at sulfur to try to get some guidelines as to what to do from this point on. So we rely on this heavily as our guidelines to try to figure out how to make agriculture more sustainable. That should be the goal. I got involved in sustainable ag because I saw what was going on in the environment. My father was born in 1896. My mother was born in 1910. And there was no cancer in our family history until the 1980s. And then my mom got cancer. My older brother got cancer. I had a sister that died from cancer. So all of a sudden there was something terribly, terribly wrong in our family, and our family had a long history of being healthy. And I kept asking myself, what is this? What is this? And I prayed and I tried everything I possibly could. I wanted to help my family. That was my initial goal. That's why I got involved in this. And I just started looking at the soils. And we are whatever soils are. Every mineral in your body, every element in your body eventually came from soil. Soil comes from rocks. So that's got to be a natural system that has natural cycles and natural things that we can actually encourage to happen. So what do? We start out with some sort of soil test to figure out where we are. Well, soil tests start out with an extraction. In other words, you put the soil in some kind of extractant, and that'll extract out something. And then it's analyzed. So there's two steps to a soil report test. First of all, how was it extracted? Secondly, it's analyzed. Well, the analysis itself, this one is ICP, the analysis itself only analyzes what is in the extraction. You might have guessed, I've got a lot of training in qualitative and quantitative analysis, so I understand this. I hope I can communicate it to somebody. That's my goal. Soil extraction chemistry was this just blew me away when I found this out. It was developed by university extension agents. Whoa, I thought it came out of the scientific literature. No, it didn't. It was developed mostly by agents. There's very, very little reference to peer-reviewed scientific studies when it comes to the type of analysis that's used to figure out what's in our soils. I was just totally shocked by that. Every lab says there is a correlation between what we report to you on the test and yield. Notice agriculture has never taken the responsibility for our health. It only takes responsibility for what we can yield. Okay, so they claim there's a correlation between those, and that's how they came up with it. Okay, there's the Morgan, developed in 1941, the Melick, the Olson, the Bray 1, which you're probably familiar with, the Bray 2, which is a stronger extractant, and there's the ETA. Do you notice a pattern here? There's a definite pattern here. Take a look at the dates. These methods were developed for high NP and K inputs. These methods were developed in a day when we weren't using the word sustainable or what is it doing to the ecology. That's where these methods all came from. Maybe it's a time for a change. The Bray, I'll just pick on one for example. The Bray extracts what they call available P. I was taught that plants only take up, literally suck up, only available nutrients in soil systems. That's what I was taught. They have to be soluble. If they're in soil solution, then plants can take them up. That's what I was taught. This test extracts what is called the available extractable phosphorus. The Bray 2, which is a stronger extractant, claims to extract out the available, which is in the P1 number already, and then they add what's called fixed P. It's supposed to be coming primarily from organic phosphorus. Phosphorus, 99.999% of the phosphorus in a soil system is in organic matter. It's combined with organic matter. It's not there in soil solution. So with that in mind, there should be a correlation between whatever they claim they're extracting and organic matter. Because if these things are primarily organically bound, then there should be a correlation there. But the emphasis that we've been all trained to do and all trained to think is on solubility of materials. If it's soluble, the bigger the N number, the bigger the K number, the bigger the P number on a package, that's supposed to be better. Well, think about what you eat. You're not any different than any other living system that's out there. I don't care if we're talking about bacteria or if we're talking about plants growing in soils. When you had breakfast this morning, how much of your breakfast was soluble? Well, the sugar in the maple syrup is highly soluble. If this bacon and eggs, there's salt in the bacon, that's sodium chloride as a salt, that's highly soluble. What do we know about salt and sugar in our diet now? What do we know? I mean, it's the best thing there is, right? The more the better. No, almost everything you eat is insoluble in water. So how do you get your nutrients? They're not soluble. They're highly insoluble in water. See where this is going? There's no difference from one biological system to another. I don't care if we're talking about plants or soils or the rumen, all these soils, all these systems, all biological systems under a microscope or chemically or physiologically or biochemistry-wise, they're all the same. We are all the same. The systems are all the same. So where did this emphasis on available or soluble ever come from in the first place? I don't know what got that started. I'm going to pick on the University of Minnesota. I can't help myself. I'm going to Minnesota for a presentation. I'm doing a little research, and I go, here's the University of Minnesota. They say, understanding phosphorus in Minnesota soils. So I thought, this should be interesting. Maybe I can show the group something about what the University of Minnesota says. And what they say is, but plants can only use inorganic phosphorus. That'd be phosphate is what that would be. Only. That's the only form they can use. Really? When 99.9999% of all the phosphorus in soils is organically bound, what are they suggesting here? Are they suggesting that you burn up your organic matter to mineralize it into phosphorus, to mineralize it into nitrogen? I think the answer is yes. That's what they're suggesting here. Because how else are you going to get that organically bound, which is called fixed or not available, tied up, goes under a lot of different terms. How are you going to get it? Okay, if the emphasis is on soluble nutrients in soils, there ought to be a lot in the literature, in the scientific literature, on how much available N, P, and K, calcium and everything else, that there is in a soil system. And I had a really hard time finding what is in soil solution. And finally, I came across it, and this is really fascinating. 0.001. That's a millimole. That's a millimole. A millimole is 1/1000th of a mole. A mole is the molecular weight of a substance in grams, equivalent to its molecular weight. In other words, it's about that much. Just a pinch of available soluble phosphorus is found in a typical soil. Now, this isn't right after fertilization. This is after the soil has settled down, or a natural soil system. This is typical. This was a global study, and that's what it came up with. Geez, not much. I think the answer is none. So I made a little spreadsheet of all that data, and I took the millimoles, and I had to do a lot of conversion and a little bit of math and everything else, and I thought, I wonder how many pounds there are per acre of these soluble, available N, P, and Ks, potassium, magnesium, calcium, how much sulfate is there, and everything else. And my spreadsheet says that there's about 0.6 of a pound of nitrate in 1 acre of typical soil, 1.6 pounds of ammonium, another form of nitrogen, the positively charged form. The phosphates, this is really interesting, P4. To a chemist, this is really interesting because the question would be, oh yeah, at what pH? Because there's numerous phosphate species. Depends on whether the pH is neutral, acid, or alkali. So that's misleading from a scientific standpoint right there. Oh, 0.0014 pounds of soluble phosphate in the soil solution in a typical 1 acre of agricultural soil. In other words, there isn't any. There just isn't any. So why would you want to put on a highly soluble form of phosphate? And I think, if you haven't heard this by now, once highly soluble synthetic phosphate is applied to a soil, it's totally tied up within 21 days. That's it. It's there. It's not gone. But our conventional science that we've all been trained to mimic says, oh, well, let's tie it up. So you got to pour on more. That's the answer. Okay, that's not much. Let me use a case study. This is how Paul and I got started. I'm going to start right where we knew each other for a while, but he called me up one day and he says, hey, Lawrence, I got this new seeding, and I'm putting on a product that I branded DTA Cal. Okay, well, nothing unusual about that photograph. I've seen a lot of new seeding photographs, and I'm not impressed. It's like, okay, there's another new seeding photograph. Did you ever notice, if you're a photographer, there's not a lot of creativity when it comes to agricultural photography. We don't, you can stand there and take a picture and that's it. What we really don't know what's going on is what's going on underground. And he said, this is applied to a new seeding. There was no cover crop. And he sent me another picture of what I thought was a pretty typical picture, this a couple of months later, or just before first cutting probably. And it says, he told me there was only 250 pounds of this put on per acre, and I'm applying it for its calcium bioavailability or availability. That got my attention. 250 pounds as a calcium correction, that's just unheard of. So that started our relationship with each other on what do we do next. He said, it's working. I want to know why it's working. So in other words, he wanted the knowledge so he could apply that knowledge to other things. So this is when we started diving into this product called DTA Cal. So this will be like a little case study to show you how we approach something when we already know it's working. That's pretty neat. And what I've been using, and Paul and I use a lot now, is what I call geochemical analysis. What we're looking for in geochemical analysis is how many elements are in there, and let's extract out as many elements as we possibly can, and let's see what this material is made out of. That's geochemical analysis. Geochemical analysis comes out of the mining industry, like up in Canada, for example. And if they're looking for parts per million of nickel or silver or gold and parts per billion, they want a really good idea as how much is actually there. So you use a different extractant than you do in typical agricultural laboratory situations. You use an extractant called aqua regia, which is extremely strong. And the geochemical analysis of his calcium carbonate, and I knew it wasn't limestone because you can't put on 250 pounds of limestone on a neutral soil and get a result. So I knew it wasn't limestone, but I didn't know what it was. Came back like this. This is I think this is everything. Arsenic, 1.7. I look at arsenic a lot, and cadmium. I want to know where the cadmium is because these two can really hold back production, but cadmium is really nasty. I mean, cadmium will hold back biological production to beat the band, so I'm always looking at those numbers. So on the parts per million, this one stands out in my opinion. It's rubidium, which he mentioned earlier, because rubidium is always associated with potassium. Rubidium is associated with potassium. The highest concentration of rubidium in the human tissue is in the heart and the brain. Very, very high concentrations of rubidium compared to other trace elements that are in your body. And there's higher concentrations of potassium in both those organs. And in working muscles have a higher concentration of potassium in them than relaxed muscles. And there's a higher concentration of rubidium in working muscles compared to relaxed muscles. So something's going on with rubidium. We just don't exactly know what it is. Strontium. I always look at strontium. The reason why I look at strontium is because it's always associated with calcium. In the absence of calcium, you don't see strontium. In any kind of natural mineral, in every soil system, in human tissue, it doesn't matter what we're studying, any biological system, if you see calcium, you should find some strontium related to that because the two interchange with each other chemically. And we think what's going on is that when there's strontium present and there's a calcium stress, for some reason or other, strontium will take the place of calcium in biological systems to modulate all sorts of enzymatic activity. So there's a reason why this happens. Total sulfur in his product was 1.32. And then there's another series of elements that I look at very, very, very closely, and that's called the lanthanide series. And when I saw the lanthanum and cerium ratio of almost 2 to 1, or 1 to 2, then I knew that it was a natural product. This is just a little thing I picked up way back when. Boron is nice boron there. Okay, so we don't look at, when he developed a calcium product in our work, I didn't look at how much calcium is there. I want to see how complex that calcium is. Okay, so that's one thing. We got a geochemical analysis. The next thing I ran for him was called X-ray diffraction, which is a non-invasive way of looking at not only the chemistry of a material, but what is it mineralogically. It looks at what mineral we have present there. Now this is interesting about calcium carbonate. This limestone here is calcium carbonate. This seashell is calcium carbonate. Marble is calcium carbonate. Calcite is calcium carbonate. Dolomitic limestone is calcium carbonate. Pearls are calcium carbonate. And aragonite is calcium carbonate. Okay. This is a series of chemicals that take on different forms, even though they have the identical chemistry. Their chemistry is calcium and carbonate. So all those that I just showed you had the same identical chemistry. But they're not, marble's not going to work trying to utilize it as a calcium source. And nobody's going to grind up pearls, but they're all the same chemically. So obviously there's something going on with the structure of these materials. Okay, what they are is called polymorphs. There's many, many different shapes of calcium carbonate, polymorphs. There's 600 crystalline different forms of calcium carbonate. Fascinating mineral. It looks so simple on paper. A little calcium, a little carbon, a little oxygen, and you end up with 600 different crystalline forms. But there's one form in soil systems that's formed naturally through biogenic processes, through biomineralization, and that's called calcite, or biogenic calcite to be technically correct. Biogenic calcite says it's calcite and it came from a biological process. That is the most common form of calcium in soil systems. Natural calcium, naturally occurring calcium, and it's formed through biomineralization. So I sent it out for the XRD analysis, the X-ray diffraction analysis, and this is what you get back for data. And this thing came back 97% calcite, and the rest of it were the trace minerals that I showed you, and ultra trace. So there it is, bam, calcite. We got confirmation that this is not limestone. These other peaks in here just say, well, there's other things in there, mostly silicon, sulfur, and some traces. That's what the other peaks say. Okay, next step. What do we have? What do we have that bugs like about this? So you got to look at the structure of it. So he showed you this one earlier with the 69 micron right across here. And this was at 1,000 magnification. That is structure. That is not a stone. That is something that has structure that is compatible in biological systems, in our opinion. Compare it, and he showed you this one too. And this is only at 1,000. You know, he showed you some scanning electron micrographs earlier. They were at 10,000 magnification, so you can see the detail. But you don't need a lot of detail to look at a rock. That is, what he didn't say was, that is 200 mesh limestone. Just bought it right off the shelf. Said, send me some 200 mesh limestone sample. That's exactly the way it looks at only 1,000 magnification, which is not a great magnification. And these little tiny specks here are just dust. Everything else is just rock. And that's limestone. A lot different than biogenic calcite. So the structure, the chemistry is the same, but the structure is totally different. It's a polymorph. And I mentioned this one earlier. What this is calcite on fungal hyphae. The point of this slide is that in natural systems, like if you use, this was a compost sample, pull a compost sample out, look at the fungi in there, and it's going to be associated with something that occurs naturally, calcite in this case. So I thought that my wife would help me on this, and she did. It was wonderful. She helped me put together this database of soil analyses from Midwest labs. You'll probably recognize up here, here's the organic matter, the P1, the P2. All these ammonium extracts are here, ammonium acetate extracts. And Paul did this thing for a while, I think he still does, called TKN, which is total, it's supposed to be a total nitrogen that's found in a soil, bottom line. Okay, it's a method of analysis for total. And we put it into a database. If you look over here, we're on line number 386. It's bigger now. We added to it. We've added to this. So 386 data points for everything on here. In order to do something that's statistically valid, you need a minimum of 40. Once you hit 40, you're into a range of validity that's scientifically valid. We're at 386 on this. Then I ran statistical analysis on all this data just to see what we got. I didn't know where this was going at the time, by the way. I just had the data. I put it all into a data sheet, and here's what we got. The pH to CEC ratio, something that Paul talked about. It's really not quite as simple as he said because it's an algorithm. It's the pH divided by the CEC plus the result of taking the organic matter minus 2, dividing that by 100, and adding it all, summing it all together. I mean, that's a tiny little algorithm, but that is what the pH CEC ratio is. So what this data says, this is what they call a descriptive statistical analysis. It's meaningful in that it's robust. You see this curve here like this? Okay, did you ever hear, I know you got graded on the curve sometime in school, right? You heard about that. We got graded on the curve. You're loud. You did so bad on the test, so I had to grade on the curve. Did you ever get that from one of your teachers? No, I did all the time. Okay. Your scores were so bad, we had a grade on the curve. What they're saying is they had to do a statistical analysis of your test scores to see what was normal, okay? And normal means that you had to fall right in this range right here. And that's described as somewhere between the first quartile and the third quartile, and all gathered around the median. This is the most robust data right here. And according to this, almost most soils fell right in here. So phone call to Paul. Paul, are a majority, would you say that a majority of the soils that you tested this ratio on, are they productive? Yes, they are productive. These are productive farm soils. Okay, that's all I needed to hear, because now I know that we got confirmation that this ratio is working. Okay, I won't bore you anymore with all this statistical analysis. The mean is 0.5, median about 0.56, and the mode about 0.51. For statistical analysis, that says that's very robust data. This is solid. This is solid. Okay, so there, I just repeated myself. All right, so I looked at this and I thought, gee, I wonder how that compares to Paul's scale. Paul says the sweet spot's right in here. I call it the potential for agricultural production. What do you call it? You got a name for it too. Okay, so what I did was I just flipped this like this, and I got a perfect match. I mean, 0.06 is right here, 0.7 is right there. Got an absolute match out of this thing, and there it is. Confirmation that if your soil is in this, what this data says is that it confirms what he's been saying out there. He's been saying that if you're in this area, your productivity is going to be good. Most of the farms in this database are productive. So this confirms exactly what he was saying. This scientifically holds up what he was saying about his CEC to pH ratio. This is the pH. Oh yeah, you always know it. I should point out this number right here. The number 379 samples. 379 samples pH right here. Okay, they fell right in here. Mean 6.8, median 6.9. Okay, this is still robust data. It's really skewed over to the right, which is saying that most of the soils that are in this database, most of these soils that are on his program that have been tested, are mostly in the alkaline range. Mostly. That's where the pHs are falling. So definitely not on the acid side. This is really interesting right here, a mean of 6.8. I don't think you can get any better than that on a potential production. The total kJ nitrogen, TKN, database consisted of 371 data points, and the range, the first quartile to third quartile, right in there is the most robust data. That means that's where most everybody is. And what that says is that there's about 3,500 pounds of nitrogen per acre on the typical soil that was tested under this program. It's there. It's absolutely there. It came out, we just plugged the data into this and then analyzed it. There it is. It's actually there. Fascinating. Mean is 16. It's just solid data. Absolutely solid. I left all the outliers in. An outlier means that's a weird one. That's a weird piece of data. It falls outside of the normal range thing. I left them in. Normally you take them out for statistical analysis to make the information even more robust, but I left them in just to show you how highly variable that information is. It's extremely variable. I mean, you have numbers down here near 400, and you got a single field up here, 2,811 parts per million of total nitrogen. I mean, there's some extreme ranges out there, but look where most of them fall. So, there's more. Paul spoke about the PT2 analysis. The PT2 analysis is another way of extracting whatever's in the soil. It's the extractant that makes all the difference in the world. In this case, TKN, the one I just showed you, uses boiling sulfuric acid for the extraction process. Okay, that's a method of extraction. That's a pretty strong extractant. But PT2 analysis uses boiling nitric acid. Nitric, you see the N, nitrogen. This is more compatible with nitrogen chemical species that are found in there. So this extractant should extract out even more nitrogen than the TKN. And this is a a report, and the report calls it Total Soil Report. And the PT2, if I recall, Jim, that's a plant tissue procedure. That's where the PT came from. So he took a plant tissue procedure and used it for soil because he knew that it was going to extract out more. And this is a nitrogen result for these fields. Then let's analyze this data. So we poured the data into the database. At that time, I only had 63 data points. For some odd reason, the guy running the lab or somebody said, oh, that's the same as TKN, and they were reporting TKN and PT2 on I don't know how many reports as the same. And I caught it right away. I go, no, you can't have identical numbers on a report. It just never happens. You know, it's going to vary by at least a few numbers, but they're absolutely identical. Looked into it. So, sorry, we only have 63 points, but we're over 40. So we got valid data. I've increased this to about 73 or 82 points now, and it's looking very much like this. The PT2 says that there's roughly 2,900 to 4,500 pounds of nitrogen per acre in these 63 samples. So that's actually a wee bit higher number than the TKN gave. So there's more nitrogen out there than even what the TKN says there is, because it extracts more during the extraction process. So that data right there says you got a lot of nitrogen in a typical soil. These are soils from the Midwest, all around here, all around Wisconsin, Iowa, and they're all lumped together, and this is what we're seeing. This is the potassium results for PT2 extraction. It says there's about 2,300 to 4,200 pounds per acre. That's all that data right in there. These are a little on the low side and these are on the high side, but the typical soil, which means there could be more out there for you, is right in the range of 2,300 to 4,200 pounds of potassium per acre. Why would you want to put on more? It's there. It's there. This one, the PT2 phos, which is, and notice I don't have that cute little orange curve on there because this is not a standard distribution. This is skewed way to the left. So this statistically that most people are on the left-hand side of this information. 276 data points. It says 574 to 912 pounds is typical of a soil in the Midwest. Interesting, huh? What are we told? We told, well, if you carry off 500 pounds per acre, you got to replace it with 500 pounds per acre. That's what we're told. Gee, I think what's happening over the years is that you're building it up more and more and more and more. Except for nitrogen. Synthetic nitrogen doesn't stick around very long. Only 17% of it gets utilized by the plant. The rest of it goes down the Mississippi River. Or in your wells. Okay, I had to break this ammonium acetate extraction method compared to PT2. I had to break it down into what's called the log 10 standardization, just so I had some numbers I could work with that made it easy. I'm not fiddling with you here. I'm just doing a log 10 instead. So I want to compare the PT2 ammonium acetate extraction and found out that it actually understates the amount of elements that are in soils by an average of 23%. This is interesting. So if you get a number from ammonium acetate extraction, you compare it to a PT2 extraction, you get a totally different result, especially sulfur. That one just jumps right out. You got 38% more sulfur in your soil on average compared to what the sulfur analysis says on a typical ammonium acetate extraction. It's almost 40% more sulfur there than what the current methods are telling us. The standard methods. But wait, there's actually more. This really gets good. We assembled what my wife and I call a global database. We want how much is in, how much NP and K and everything else. Well, skip N, that's too highly variable. How much is in the typical soil throughout the entire world? Then compare that to Midwest soils and everything else. So it took us about 2 years to assemble this database of what elements are in soils globally. And it turns out that compared to PT2, almost everything on the PT2 is still understated. Because if you use a stronger extractant, which Back to geochemical analysis, use an aqua regia extractant instead of the boiling nitric acid, you actually extract more elements out of the soil, and you get these kind of numbers. Numbers such as the PT2 test, log 2.2 compared to log 3 is a 28% difference. There's even more sulfur out there than what I just told you previous to that. And it just gets better all the time. So depending on the analytical method you use, that's going to determine what the report says. There's 22% more potassium out there than what the PT2 says. So he's pushing the PT2 test. That's fine. It costs a certain amount of money that anybody can afford, but you don't want to do this analysis because it's really expensive. But the good news is there's more out there than what it really says on the PT2. But the PT2 is a better guideline, in my opinion, than what we're getting right now from the ammonium acetate. And like Paul said, if you're going to still use the ammonium acetate report, okay, if you've been using that for years, let's start there. Good way to approach it. The global database says that there's 550 parts per million of phosphorus on average throughout the whole world. And these variations are not that tremendous. Surprisingly, most soils of the world look about the same when it comes to elemental composition. That means that there is, okay, this I forget what my point was there. Anyway, I'll just go to the next one. Okay, there's about 10 times more potassium on a geochemical analysis than actually the PT2 reports. So there's even more potassium out there than what I threw out earlier at you. There's 1,300 compared to what we were on this. I go all the way back to slide number 1 now. It said, if you have 20 parts per million, you're high. Well, the average soil in the whole world has 1,300 parts per million of sulfur in it. So I don't see where 20 is high, because that was supposed to be correlated to crop production, right? And that's not even based on science. It's based on opinions from extension agents. What a history we have. Now, he mentioned it, the calcium to magnesium ratio. Okay, I was trained that the calcium and magnesium ratio has to be 5:1 in order for you to have productive soils, disease-free soils, all that sort of thing. Honestly, I don't know how you would ever get there, unless you want to put on like 52 tons of some kind of calcium. That's calcium, not calcium carbonate, but calcium elemental. So I don't know how that even translates out into CaCO3. It's 100 tons maybe or something. Anyway, globally, all soils in the world are about 2:1, 2.2. 2.2 is what I got here in the Midwest. Globally, about 2.3 is the ratio. And I don't really know if you really want to try to control that. You know, you would take a lot of calcium input to shift that number. It would take tons and tons and tons of calcium to move that number. Now, the oddball, potassium. I always think it's so odd. Potassium behaves in a way that no others do. Potassium is not related to organic matter. Just isn't. Most everything else is, but it isn't. Potassium becomes part of minerals that are actually in there. It's adsorbed by minerals that are actually in the soil. And the only available potassium, that number, that really, really little number, it's right on the very edge. You get a total potassium number on a soil analysis, and then you try to figure out what's actually in soil solution. Very, 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 very little is in soil solution. So how do you get it out of there? What you do is you generate biological activity in those soils to extract it. Bugs are the only thing that can get in all these little crevices and everything, because that's their job. Their job is to seek out. Remember how we showed the fish flying back down, you know, scurrying back down into the coral reef? Same thing happens in soils. Microbes know how to access potassium. Cover cropping helps tremendously because it puts the right type of enzymes and bioavailable materials into a soil to kickstart and keep that biological process going. That's how you get potassium out of soils. And there's a lot of potassium in soils, in the typical soil. Run a PT2 test, run it, you get a number. It's a surprisingly large number. And guess what? There's even more than that out there. That's just what that test says. So on geochemical analysis, what we're looking for is elements, complexity. Our opinion is that the more complex an input is, the more likely it's going to work in a biological system, because biological systems rely upon very, very complex interactions in order to pull off what their job is. So we're looking for complexity. Well, this is the gift, if I remember right. And the gift has potassium in it, rubidium. Look at that relationship. Wherever there's potassium, there's always rubidium. Always. You know when that was discovered? You know when they discovered that potassium interchanges with rubidium in systems? It was discovered by actually experimenting on human cadavers, on human tissue, and analyzing them for potassium, and analyzing them. And they always noticed that rubidium was present. So the conclusion was, oh, potassium and rubidium probably interchange with each other because they're on the periodic table right next to each other, so they're chemically very, very identical, and so they interchange. That was in 1885 that they had that figured out. Go figure. Boron is in that product. Oh, someone's going to notice sometime soon that this is in parts per billion. That's 1,000 times less than parts per million. And you're going to think, that's not much. That's right. Think about it from a microbe's perspective, though. There's hundreds and thousands and millions of these molecules being put in the soil. And we look at it as not much. But from a microbial perspective, it's there and it's utilizable. Wherever you find calcium, you always find strontium. There's always a relationship between calcium and strontium. In any kind of biological system, if you're analyzing human tissue, or if you're analyzing soils, or if you're analyzing natural minerals, you're always going to find calcium and strontium associated with each other. Not so much in limestone, though, for some odd reason. Don't know why that is. Just the way it is. Limestone's peculiar that way. There's magnesium in the product. There's silicon. There's phosphorus. And, the list goes on and on. Lots of sulfur, plenty of sulfur. Sulfur is generally over-applied, in my opinion, because sulfate is very disturbing to biological systems, including water use efficiency. Okay, then there's a group, chromium. Why would anybody want to look at chromium? Did you ever hear of diabetes and insulin resistance? It's usually it's usually a deficiency in chromium in your diet that starts that whole process, aside from the fact you ate too much sugar. But it's chromium that regulates the enzymes necessary for that. So I thought I'd throw a little note in here. Chromium increases the bioavailability of copper. It increases the bioavailability of boron, nickel, and it regulates imbalances in iron, manganese, and vanadium. So just one little thing like that has all those functions in biological systems. And look at all of them that are on there. I just picked on one, just one. What does it do in biological systems? It does a lot of things. So it turns out that chromium is also needed for nitrogen fixation in soil systems. So is cobalt. You ever ask for cobalt to be put on your soil? Molybdenum. If there's no molybdenum, you're not going to get nodulation. If there's no nodulation, you're not going to get nitrogen fixation. And it all goes back to cobalt and molybdenum being in the soil at very, very low concentrations, 1 to 4 parts per million. That's all you need. It doesn't take very much at all to make that system work. Nickel is absolutely necessary for the enzymes that are involved in nitrogen fixation. Who puts nickel on their soils? Nickel, according to the United States government, is only needed by pecan trees. Well, it's been my experience that if a pecan tree needs it, we probably need it, the soils probably need it. How can you isolate something like that and say, oh, just pecan trees? Because the powers that be are so stubborn to move away from where they've been for so long, they need a big, big pile of evidence like this. And I was there the day that they approved nickel as an essential, as they like to call it, essential element for pecans. Well, I'd rather get some nickel rather than wait for the law to catch up. Tungsten and vanadium are also critical to nitrogen fixation. And you just never hear this. But what they are there for, what they do is they are enzyme cofactors. If you have an enzyme, you wouldn't have an enzyme if you didn't have these enzyme cofactors. Let's put it that way. Enzymes won't even be created in the absence of these. If vanadium is present, then you will get the enzyme needed that participates in nitrogen fixation in these biological systems. In the absence of vanadium, vanadium literally activates the enzyme. So these are enzyme cofactors. All of these are. Many of these are. on this whole thing here. Then there's a series of elements that I get really excited about because one of the first things I ever did was meet a very brilliant geologist up in Ontario, Canada, and he talked about the lanthanides all the time. He said they're actually enzyme cofactors. He said they're very, very critical to catalyzing interactions in biological systems. And finally, the literature came out last month proving him right. And that was like 15, 20 years ago when he told me that. Brilliant guy. Lanthanum, cerium, these are the highest concentrations in lanthanides. Dysprosium, erbium, europium. We have gadolinium. Gadolinium, I don't know if you ever heard of that one or not, but if you go get an MRI, they inject you with gadolinium, by the way. that's what's in there. Very, very reactive, interesting element. Neodymium. Neodymium is used, by the way, China controls all these on the open market. And neodymium is used extensively in supermagnets. Praseodymium, samarium, thulium. The only one missing here is thulium. And it just happens to be in very, very high concentration in its premix. So if there's something missing here, it's made up for in the other part of the program. It's highly, there's a good enrichment of holmium in another product. So it's missing here, but it's in another part of the program. These are what these things do. Yttrium is usually considered a lanthanide. I don't know why. Its chemistry is very similar. You know why these are needed in biological systems? You hear all about calcium. Calcium does this, calcium does that. And if you have calcium, you got to have boron. Well, guess what? They do not become activated. The enzymes that are there to utilize calcium and the secondary modulating, all these signal systems and everything else, they're all pretty much dependent upon those elements right there as being present. And some phosphates have a really high not phosphate, rock phosphates. Some rock phosphates are highly enriched in these materials. They're also highly enriched in rock dust, granite dust. Remember, we all came from the soil, so if you were looking for something, that's where it is. It's in the rocks. That's where it all comes from. Here's the periodic table. Much to my surprise, there's no standard periodic table. I didn't know that. I've been a chemist all these years. I had no idea there was no standard periodic table. This is what everybody sort of agrees upon right now as the periodic table. It's got 116 or 118 elements on it. And this is the year of the periodic table, by the way, 2019. So anyway, the IUPAC, the International Union of Pure and Applied Chemists, are getting their heads together right now trying to come up with a standardized periodic table. And boy, they got some really weird looking things they're calling the new periodic table. I hope they don't go that way, because this periodic table is based upon the chemistry of each element, how they relate to each other. So lithium acts very, very much like sodium. Sodium acts like potassium. Potassium acts like rubidium. Rubidium acts just like cesium, and vice versa. Chemically, they're all very, very, very close. Anything in red is radioactive. Synthetic. And if it's radioactive, we put that little symbol on it there. And the reason why mercury's in blue, because I don't know what mercury does in biological systems. I have no idea. There's no research on what if we take all the mercury away. Will we survive? Will a rat survive? Will a mouse survive in the absence of mercury? No one's actually run that kind of testing. We all know about the toxicity of mercury. We used to play with it in high school and roll it around on the floor and everything, just have fun with it. But we don't know if it's essential. Now, notice arsenic's on there. If you don't take in roughly 4 to 5 parts a million of arsenic per day, you will not be healthy. Arsenic is essential to your health. And if you take arsenic out of the diet of a rat, for example, it doesn't do well at all. You take it out of the diet of livestock, they don't do well at all. It's necessary. Arsenic gets a really, really bad rap. And they say it's a heavy metal. It's not even a metal. I don't know where does this stuff come from. Anyway, we looked at all those elements, all 116 elements. We said, which of those elements do you think are absolutely necessary to biological systems? And I call it Paul's periodic table. The answer was 75. You start adding them all up, you go across here, and your answer is 75. Okay, Now, either we're crazy or we're being supported by science. Luckily, there's an emerging science coming out. It's only 4 years old. It's called the science of elementomics. It's another one of those omics. There's metalomics, and now there's elementomics, which says probably every naturally occurring element on the periodic table, with the exception of radioactive elements, is probably necessary for living tissue. And every year, a new one ends up on this elementomic approach as being necessary. Like I just said, last month, they finally figured out that lanthanides are absolutely necessary. Now, take that to a regulator in Minnesota and try to sell it to them. Put that on your tag and try to sell it to them. They won't believe that for a minute. We cannot guarantee 75 elements on a tag because they have to be proven to be essential and they have to be guaranteed in minimum amounts. And I don't think that's the case anymore. These minimum amounts got us into trouble in the first place. I think they need to be there. I think if they're there, the biological systems will figure out a way to use them. I think I have too much iron. I hear that all the time. Well, guess what? Iron is like the number 2 or 3 thing in our whole universe. How are we going to get rid of it? Yes, there's iron. It's everywhere. It's everywhere, literally everywhere. It's probably one of the largest, except for silicon and aluminum. You got a lot of iron in your soil, I guarantee you, and it's there. So what do we do about it? Okay, well, next step that I took on that huge database was to do a correlation analysis of those 300, 400, 500 points, whatever it's up to now. And I took this information here, straight off of the the reports right here. This is your ammonium acetate stuff. And then I ran a correlation analysis. And anything in blue means that it's slightly correlated. It has to be correlated more than 0.5 in order to be a correlation. And most scientists won't accept 0.5. When it gets up around 0.6, then they say, yeah, there's a correlation there. But 0.5 only says these are correlated 50% of the time. That's what 0.5 correlation analysis says. And I did the long form of this at a presentation, but what I ended up doing is Xing out every darn one. There's no correlation between all of these tests on the top, except for calcium and TKN. Otherwise, there's no correlations there whatsoever. Well, wait a minute. They're supposed to be correlated. They should be. Yeah, I just showed you the periodic table. Anything on the periodic table is correlated with anything that's above it or below it. So there should be a correlation on how we extract it. The correlation should be consistent with nature. Well, they're not. But check that out. 0.9 correlation between TKN and organic matter. That's interesting. Very interesting. Okay, just so I don't lose you. Here's a correlation. Let's say you have an ice cream stand and you sell ice cream cones. Every day you write down how many ice cream cones you sold for the day, and you also note what temperature it was. Well, gee, it takes a genius to figure out that when it's cold out, you're not going to sell many, and when it's hot out, you're going to sell a lot more ice cream cones. Well, guess what? That can be analyzed. That can be correlated. So on the bottom here, let's put some kind of temperature, and then on the left-hand side here, let's put the number of ice cream cones sold per day. And as the temperature goes up, you begin to see a relationship. But it's not a straight line relationship. It's not perfect. You get this odd one sticking out here, odd one there, odd one there. I don't know. Was it exceptionally hot? Or was there a band playing on the street and you pulled a lot more people in that day? We don't know why you sold a heck of a lot more ice cream cones in that day at almost the same temperature as that day. But to be statistically analyzed as correlation, you need a lot of data. You need a big chunk of data. And if you start keeping track of this over a long length of time, you keep plugging your data in, you start seeing what's called a scatter chart. Notice there's no perfection here. There's some here, there's some there, there's some there. Okay, and as time goes on, you get, let's say, 368 data points, for example. Then you start seeing a pattern, a graphic pattern. That circle says 75%, which is that quartile thing all over again. 75% of the data falls right in here. So we can say there's a correlation. Well, mathematically, it needs to be calculated using the Pearson's R. Temperature versus ice cream cones, in this case, is correlated at 0.6. So 66% of the time, I can say temperature drove sales. I think that's a pretty good correlation. It's above 0.5s, and it's very likely that when you sold an ice cream cone, it was 66% odds that it was warm out. That's what that data says. That's correlation analysis. Now let's see what we got on the soil database. Some people put a line through it. And if that line is perfectly at exactly 45 degrees, that's a near perfect correlation. So what about the Bray? The Bray P2 is supposed to be an extraction of organic matter combined, phosphorus and organic matter. And so there should be a correlation between how much Bray 2 you extract, and there's 377 fields that were tested here in this data place. The Pearson's R coefficient says none. No correlation whatsoever between the organic matter that's in a soil and how much P2 extraction you get. You go, wow, how can that be? I've always been told that 99 or 97, there's all these ranges, percent of the phosphorus in the soil is organically bound. But how come there's no correlation between the soil test and the amount of organic soil, the organic matter in a soil? Well, that just says it's not valid for that purpose. That's what that says. It's unsupportable. Then you look at the TKN that was run versus the organic matter content ranging from way down here less than 1 all the way over here to greater than almost 6% organic matter. There is a correlation running right through here, a very, very tight correlation, a correlation of 0.924. That's almost unheard of when it comes to correlation analysis. I mean, that is a rare day when a scientist sticks a bunch of data together and comes out correlated 0.9. Holy cow, I've never seen a number like that, ever. That is strong. That says, okay, what are the implications of that? If Paul says, as you build your organic matter, you build your nitrogen, he's absolutely, positively right. You can take it to the bank, because there is scientific evidence that what he's saying is absolutely true. 370 samples in that data right there. Amazing. I'm amazed. I've never seen such a strong correlation between two things before, ever. The correlation between PT2 nitrogen and organic matter is almost as strong. It'll round off to 0.9. I mean, holy cow, that's fantastic. That is consistent. That's confirmation that both extraction methods correlate to the amount of organic matter that's in a soil. Here's the organic matter versus PT2 sulfur. Bam, again, strong correlation, almost 0.8. Excellent, excellent correlation. So yeah, as you build your organic matter, you actually will retain more sulfur into the soil. I'm not saying it got there through transmutation or something like that. I'm not saying it was created. I'm saying it's been retained for some reason. It's not being carried off. It's actually building. As the organic matter builds, so does the sulfur, so does the nitrogen. Now, soil analysis for organic matter concentration is a rather sad report, except for Minnesotans. In this database of 268 soils, they're just averaging a little bit over 1.5% organic matter. That would be the average through the whole Midwest. That means there's a lot of them on the left side here that are really skewing it over to the left, and that's the reason why there's not a standard distribution curve, because the mode, I don't have mode here, most of them are right in that range right there, 1 to 1.5. That's 95 of those samples were in that range. Okay. If we're going to build nitrogen in soils, and if we're going to build sulfur in soils, and we're going to build everything else in soils, we need organic matter to do that. The evidence says you've got to build your organic matter. That's like prime directive. Organic matter has never used to be that low, but after putting on high inputs of NP and K and mineralizing the organic matter, burning it up, this is where it's headed. It's headed in the wrong darn way. Minnesota is pretty lucky, because you're over here pretty close to this 4 and better. Now, the magic about 4, I will explain it. At 4% organic matter in soil systems and on, the cation exchange capacity, the ability of plants and microbes and all living systems to exchange nutrients is done through a balance of microbiological activity, organic matter, and clays, primarily humic substances and clays. Below 4 is an indication that the humic substances, the substances that are highly stable carbons in soils, probably aren't there as much as they should be. And now the exchange of nutrients is being relied upon another component in the soils, and that component's called clays. However, clays start out as very high energy clays like Mount Marilanite and Illites and all these sort of things, and then they get oxidized over this, utilizing this low organic matter, high input system down to the point where they become kaolinite, and at that point they lose most of their ability to exchange nutrients naturally because the biology isn't there anymore. That's what that says. That's called soil weathering. In Wisconsin, the soils have weathered an equivalent of 10,000 years in the last 40 years. 40 years of agricultural production have weathered Wisconsin soils equivalent to 10,000 years of natural weathering. In other words, destroying the soils. They're going away. What's the correlation between organic matter and potassium? There isn't any. There just isn't any. I've always been told that potassium is not associated with organic matter. Potassium is associated with the minerals in the soils. There's proof that's true. Got 264 data points up here, and they say no correlation, just none. So I got really curious about something. Paul says, I put very little on and I get a result. Really? Well, that's contrary to standard thinking. More on, more results. Okay, he puts less on and gets more results. How's he doing that? Okay, so I found this data on, and then I made this correlation, of course, between the soil element concentration and the root soil ratio. If the root soil ratio over here is high, like that dot right there, that says that that thing took up 5 times more out of the soil than what's in the soil. The soil concentration of that is way down here, or come on down here. Soil concentration, these are logarithms again, is probably about a couple of parts per million, something like that. Okay, so if we look at the ratio of the concentration of the elements found in the roots compared to the concentration found in soils, and then look at the correlation of the two, what is it? There is none. There's no correlation. Wait a minute. There's no correlation, according to this data, as to how much is in a soil system and how much the plant root takes up. There's no correlation. Oh, come on. You put on more boron, you see more boron taken up. You put on more of this, you see more of that taken up. And then you read the literature and you find out that the literature is all done in soil solution chemistry, not in soils. It's done in soil solution chemistry. That's where they came up with all this information they've been feeding us all these years. Why not go into a soil and do like I did? Just take some numbers and see how they correlate. And they don't. They don't correlate. That's absolutely fascinating to me. This plant took up 5 times more cesium than there is in the soil concentration. By a ratio. Ratios. Just looking at the ratios. Cesium. You ever heard of that before? Probably not. Rubidium is taken up much, much more than the concentration found in soil. And potassium. Ooh. Plants, what this says is that plants have the ability to take care of themselves, is what it says. It doesn't matter how much potassium there is in the soil. This thing is capable of taking up more potassium. The potential is there to take up more potassium in the soil than there actually is in concentration numbers, the ratio. You know what's interesting about all that? You go to the periodic table. That's where all of our chemistry comes from, is the periodic table. You see the potassium, rubidium, and cesium are directly related to each other chemically, and this plant was able to take up cesium, rubidium, and potassium, and they're always associated with each other in any biological system, greater than what the soil test would have told you it was capable of doing in the first place. The lesson is, the plants and the biology and the microbes, they can all take care of themselves. I got too much aluminum in my cell. I got too much iron in my cell. You know what that says? Doesn't matter. Plants took care of themselves. They took up very, very little of these two potentially toxic materials. They take up very, very little. Look at down here. Mercury, silver. Silver is highly toxic at certain concentrations. Cadmium is just about always toxic. And mercury, we know, has a high toxicity. This plant took up very, very, very little of those. It took care of itself. or the biology or the relationship between the plant and the root took care of themselves. Took it one step further. What about the correlation between the root to soil elemental concentration? Now, let's analyze roots, let's analyze soil, and see how they're correlated. None. Absolutely none. There's no correlation between what is in the soil and what's found in the root. You're more than likely going to find a higher concentration of elements in the root, because that's the first place they're going to go when they're taken up. There's no correlation. In fact, it's kind of negatively correlated. Boy, that's interesting. I don't, it's like, who's going to believe that? But there's the data right there. So that's my presentation. Hope I generated some questions. And the big question is, how much do you really have to put on? And what I'm learning from Paul over the years is you put it out there, and the system will take care of itself. As far as parts per trillion and parts per billion in the gift product, he said, it rains on plants, doesn't it? What's in rainwater? Trace, ultra-trace elements. They're there. Okay. Thank you.